So last time we talked about bonds. Let me go ahead and review bonds, but then we'll do something new. We will be talking about bonds throughout the semester, by the way, and other finance applications. So let me just do a quick review of bonds, and then we'll talk about something else. So a bond is an investment where for a certain price P, an income stream can be generated. You pay something right away. You are investing, giving money either to a corporation or a foundation or a church or the government, giving them some money and expecting a return on your investment. You expect to get more money back than you invested. And with bonds, the way you get that money back is not just with some final amount at the end, but also with these coupons in between. Coupon amounts are F times R, where F is called the face value of the bond. For corporate bonds, it's often $1,000. And R is the coupon rate, a certain percent per period of time. Again, I did say most bonds, the periods of times are half years, but maybe just for the sake of simplicity in this class, we'll typically assume it's yearly, annually, just for the sake of simplicity. So in that case, R would be a percent per year. And a final redemption value of F, in addition to the last coupon at time N. So N is the number of periods, years, say. It's also the number of coupons, starting at time 1, then time 2 through time N. The periodic yield, I, is in a sense, you could think of it as an interest rate if you want. And in fact, bonds do advertise themselves as having a certain interest rate, but they call it a yield. It's a value of I that satisfies that equation. And remember where this equation came from. I drew a number line. I won't redraw it. You take all the payments and you find their present values at time 0. It's called discounting. Their present values at time 0 are found by dividing by powers of 1 plus I, which makes those smaller numbers than F times R, right? Well, I is typically positive. You would hope it's not negative, though in theory it could be. You would hope typically I is positive. So when you divide by 1 plus I or 1 plus I squared, you get getting smaller numbers, as in fact they get smaller and smaller. And this final amount here goes back N periods. It's not necessarily the smallest thing because you also add F up there for the final face amount, which is again typically 1,000. You can turn this into a polynomial in V if you let V be 1 plus I to the negative 1. You get an nth degree polynomial in this unknown V. I is called the interest rate or yield rate. V is called the present value discount factor, because you multiply by powers of V to get these present values. Multiply factor. Discounting means you're getting these smaller present values than the original amounts. We can apply the same kind of ideas to more general cash flows. So this is new. Okay, so let's just make up an example. Suppose you invest, I said pay, invest $100 at time 0. Yeah, I'm saying pay, but think of it as an investment. You receive $110 at time 1, pay another $100 at time 2, and receive $120 at time 3. So this is not a bond anymore. It's some sort of weird investment scheme. Do such investment schemes exist? Yes, though they probably wouldn't involve such small amounts. They could exist, for example, if you are an investor in a new company, a new corporation, and they're needing some cash. They're trying to generate cash at different times, like time 0 and time 2. But you want a return for your cash, and not just in stocks and dividends. Maybe you want them to actually pay you more than you received. So you come up with some agreement where they give you 110 at time 1 and 120 at time 3. So in total, you have invested $200 and you're getting 230 back. The overall interest, you could say, is $30, though it is occurring at different times, 10 of it at time 1 and 20 of it at time 3. What's the yield rate for that kind of a transaction? In this kind of context, more general cash flow, it's not always called a yield rate. It's sometimes called an internal rate of return, IRR. But it's effectively the same idea as yield rate. And in fact, for bonds, you would call it yield rates. You need to come up with what's called an equation of value. One way to do that is to equate present values at the unknown yield rate, I. It's not the only way to do it. You could also equate what's called future values at some future time. But mostly to stay consistent, people think about present values. What are the values of these transactions at time 0? So before I show you the answer, let's make a number line. A timeline for these payments. Time 0, 1, 2, and 3 are the periods of interest. You could have an outflowing money and inflowing money. Outflowing money says, it's like making a payment. Hey, that money's gone. So I'm making that red because you feel sad about paying the $100 there. Inflowing money, I'll put in green. That's money coming back to you, so you're happy. And green means go and red means stop. Green good, red bad. Oh, sorry. If I like red. I'm not biased against red here. At time 2, there's also outflowing money of 100. But at time 3, there's inflowing money of 120. The present value of 100 at time 0 is 100 because it's at time 0. The present value of this 100 at time 2 is 100 v squared, or 100 over 1 plus I squared. The present value of 110 at time 0 is 110v, same as 110 over 1 plus I. And the present value of 120 at time 0 is 120v cubed, 120 over 1 plus I cubed. The equation of value comes from setting the sum of the inflows equal to the sum of the outflows. And the yield rate, or internal rate of return, is indeed the value of I where those are equal. So coming back here, there's our equation of value. It can also be written in terms of V. Let me just double check that it looks right. So that the left-hand side numbers are the outflows, which occurred at time 0 and time 2. The right-hand side numbers are the inflows, which occurred at time 1 and time 3. Cubic in V. By the fundamental theorem of algebra, we know that we'd have exactly 3 solutions, at least one of which would have to be a real number, right? Because it's cubic. Cubics have to cross the horizontal axis. 2 of which could be complex numbers, or they could be real. Could be repeated real root as well. And evidently, since V and I are intimately related, there must be also 3 values of I that work. And if you use Mathematica, for example, to solve for these, there are your answers. However, yeah, you can see that in both cases, there are two complex ones. The okay, this is a little unfortunate here. The I on the right-hand sides are the imaginary units. I squared is -1. Maybe we should be like electrical engineers here and use J. Electrical engineers use J for the imaginary unit because they reserve the letter I for current, because current starts with an I. Capacitance starts with a C, so they leave C for capacitance. They got to use something else for current. They use an I. Why? Who knows? But that means they got to use something else for the imaginary unit. But I went ahead and used I here on both cases, whereas over here on the left, the I represents the yield rate. These I's are the imaginary units. So I just realized that. Make a note to yourself. But how can complex interest rates exist? How does that make any sense? Well, it doesn't really make any sense unless you allowed complex number money, which we don't. So it makes the most financial sense to use the 14.3% for the yield rate. And you can and probably should after class check that answer with both your calculator and mathematics. But for the moment, if you're taking notes, you can write it down. And you can graphically interpret these. If we did take the time to make graphs of these functions, we would see these two functions of I cross when I is 0.143. And these two functions of V cross when V is 0.875. Take a time, I won't do that either. I believe you could do it. All right, you guys can. And you probably should as well. Right? I guess I'm being kind of commanding there. You should, wag my finger, take the time to double check those numbers. So if nothing else, for sake of confidence when you do your homework.